In this video, we'll take up the wave called sound. Sound is a longitudinal compression wave in air. The source of sound is a vibrating object. So we've talked about oscillators previously, and when one of these oscillates in air, it gets the air molecules to start oscillating, and these air molecules will longitudinally be disturbed, causing a longitudinal disturbance, which is called a wave. Now, you could watch or attempt to describe this in terms of the displacement of air molecules, but it's difficult because we do not actually detect the air molecules themselves. What we detect is change in air pressure. So instead of plotting the displacement of air molecules, we usually plot changes in air pressure because this is what we can most easily measure. So most textbooks will, including Giancoli's book, has some form of a picture with time on the horizontal axis, and they will plot displacement. So you could have the displacement of the air molecules. Remember that the air molecules are actually, for instance, maybe going this way, oscillating, and that's the direction of the propagation. So this is the amount that they're pushed horizontally. It's not meant to say that they're being pushed vertically. And then they give you a plot of what the air pressure would look like. And what's interesting about this is that when you have a node in the displacement, you have an antinode in the pressure. So the pressure will be a maximum or minimum, and then it will come up so that it's a node when the displacement's maximum. And then it'll go up to its max, back down to a node, to an antinode, back to a node, to an antinode, to a node, and to an antinode. So the blue represents pressure. Not that that's the world's greatest plot. Key points is node in displacement. That is, there's no displacement of the molecule, will correspond to an antinode in pressure. Either molecules nearby on either side have been moved off and the pressure has dropped, or more molecules have been pushed closer to those that didn't move, causing the pressure to go up. And an antinode in displacement will correspond to a node in pressure. So they're directly related. So measuring the blue curve is the same in a way as measuring the green curve, the displacement of air molecules, which we can't do easily. But they're not in phase. They're shifted a quarter of a wavelength. So there's a quarter of a wavelength shift between the two plots. And like I said, the maximum minimum pressure, which are the antinodes, occur when there is nodes in the displacement. There's often some sort of questions like in UIL and things on those sort of stuff. And likewise, there's questions on the AP exams. Compression corresponds to a higher pressure. So when you compress the molecules together, you'll get a higher pressure. And when you get expansion, that is, you pull the molecules apart and the density drops down, sometimes called refraction, this corresponds to lower pressure. They're still antinodes. Now the speed of the sound wave turns out not to be constant because, like all waves, it depends on the medium, in this case on the density of the medium. So the changes in the density will cause changes in the speed of sound. The speed of sound can be approximately described in air by the following formula. About 331 plus or minus 0.60 times the temperature. This is in meters per second, where T is in Celsius. So if it was at 0 degrees Celsius, the speed of sound would be about 331 meters per second, but at higher temperatures, the gas expands and becomes less dense, and when it becomes less dense, it actually causes this to have less inertia, and so it speeds up. So at 20 degrees, which is kind of room temperature, the speed of sound is around 343 meters per second. On most of your sonic rangefinders that one finds in physics labs, there's actually a calibration button to calibrate for the changes in the speed of sound from day to day. Loudness. Now, loudness is related to the human's ability to hear sound. We say sound is loud or sound is soft. But that's not just related purely to a physical quantity, but also to our perception of sound, which is due to our eardrums, which create signals that our brain then interprets it. So loudness is a human quality, if you would. It deals with the sensation in our consciousness of sound, but it is related to a physically measurable quantity, which is intensity. So if you increase the intensity, we will say that the sound gets louder. But it's not a linear thing. If you double the intensity, we won't say that the sound doubled in terms of being louder. Humans have a great range of hearing. We can hear intensities that differ by 1 times 10 to the minus 12 watts per meter squared, all the way up to about 1 watt per meter squared. And I mean this without pain. It may be possible to hear, of course, louder sounds, but you'll damage your hearing and possibly cause great pain. So if it's within the frequency that we hear, and we'll talk about that in a little bit, we can hear really low-level sounds to really large sounds. This is 12 orders of magnitude. What a magnificent range. But because it's 12 orders of magnitude, that's a 1 with 12 zeros. We're not very sensitive to changes. We have a great range, so we've got this great range, but we've given up sensitivity. So our system, in order to handle that large numbers, does not do it linearly like a straight line graph. It uses a logarithm detection system. So our auditory system, our hearing, is logarithmic. Rather than linear. And that means that if you double the intensity, you don't double what we call loud, because the log of 2 is not 2. So we're going to require a much larger increase to get a factor of 2 in terms of it being loud for us. So the trade-off for us is that we're not as sensitive to changes in intensity, and in fact it takes a 10-fold increase in intensity just to change it by a factor of 2 in what we call loud. So we say, boy, that's twice as loud. It's really 10 times as intense of a wave. Another really interesting fact. Now, logarithmic detectors are not unique. We build them in engineering and in physics, but you probably haven't dealt with them that much, except for the one that you're built with in terms of your ears, which you didn't know was working that way. Now, one of the guys who studied early on about the nature of hearing was Alexander Graham Bell. And so Bell devised what he's going to call the sound level, and we're going to give that the symbol beta, and it's going to be a measure of what is loudness. So it's a logarithmic scale, and it's measured in the decibel, or dB, and that's 1/10 of a bell. Notice there's only one L in the bell, but it's named after Alexander Graham Bell, who had 2 L's. The equation is that the sound level is 10 times the log of the intensity to some reference intensity. And this is in dB. Now, if you're just looking at relative intensity, it's twice as loud or something, you just take the ratio of the intensities. If you want to give it an absolute scale, we need a reference, and that reference is usually taken to be the threshold of human hearing, which is the lowest amount we can hear, 1 times 10 to the minus 12 watts per meter squared. So let's do an example problem. If the intensity of sound wave changes by a factor of 10, what is the change in sound level? Well, we already know the answer to that, we think, so let's see what that happens. Beta is equal to 10 times the log of 10, which is going to be 10 dB. Notice I was equal over I naught was 10. So you get 10 dB changed. Now, be careful. Let's look at the second one. If I over I naught had changed by a factor of 2, what is beta? Well, beta is 10 log of 2, and that's 3 dB. So these things are not linear, okay? This is a scale system, a logarithmic scale system developed as a way to measure sound over these incredibly large ranges. Some things to get you to know: 2x corresponds to 3 dB, 10x 10 dB, 20x I'm sorry, not 20x, 100x 20 dB. If the sound increased by a factor of 1,000, that would be 30 dB. Notice that it's 10 dB per 10x. So every time you multiply by 10, you get an extra 10 dB. 10, 10 squared, 10 cubed, 10 to the 9th would be 90 dB. All right? This is just the nature of the logarithm. The logarithm gets you this number, and then you multiply by 10 to get the beta. Humans are sensitive to changes on the order of about 1 dB, possibly 2. So that means you have to have an increased approximately 30% to 60% change in the sound intensity in order for you as a human being to notice any change at all. So you're not very sensitive. Finally, the last thing about loudness: sound will fall off with distance as the energy of the wave spreads out. For an open area, it falls off as 1 over r squared because that's the surface area of a sphere. But at really large distances, there's random motion of the air molecule, and consequently it actually falls off a little faster due to energy being lost in this irregular motion of air molecules. That's it for this video, and we'll come back and talk about other properties of sound.